Hello and welcome to our final presentation. Our project is titled Predicting Dysglycemia in ICU Patients Using Machine Learning. This was completed as part of our capstone project at RMIT University, Group VC499. Dysglycemia, which refers to abnormal blood glucose levels, is extremely common in ICU patients and often leads to severe complications or even death. Current systems in hospitals detect dysglycemia after it has already occurred. Our project aims to shift from this reactive model to a proactive one by using machine learning to predict both the onset and reoccurrence of dysglycemia. In order to accomplish this, we used the publicly available MIMIC IV dataset, which contains anonymized records. Our main objectives were to build predictive models using the MIMIC IV dataset, addressing challenges with irregularly sampled time series data and exploring both traditional machine learning and deep learning approaches. We also placed a strong emphasis on ethics and reproducibility throughout this project. A major challenge we faced was inconsistent lab measurements. The lab measurements are not recorded at regular intervals and are not consistently measured across every patient. This made it hard to apply a wide range of models, including common time series models like long short-term memory without major pre-processing.
Prior to model development, we underwent a thorough literature review. This allowed us to educate ourselves on the issue and identify any gaps in the previous work that has been done for classifying dysglycemia. These gaps would provide the motivation for the project and ensure our work is novel. The first key gap we found was that irregular ICU time series data was rarely tackled directly. Instead, continuous glucose monitoring and perfect records were overly relied upon, which is not indicative of a real-life setting. Therefore, we strive to incorporate irregular data to create a more generalizable model that is also more applicable in clinical settings where readings should be anticipated to be irregular and inconsistent. Furthermore, diagnostics following hypo and hypoglycemic events were not considered as features in the literature, so we aim to explore their effectiveness in enriching models to better classify or predict dysglycemia. The models tested included linear and logistic regression, random forests, support vector machine, extreme gradient boosting, long short-term memory, and a split LSTM using features from pre and post decompensation. For our deep learning approach, we resampled the data and built both univariate and multivariate models with up to 10 features. We also created two separate models, one using only pre-decompensation data and another using pre and post decompensation data. For non-time series models, we used aggregated patient vitals and structured glucose data into rolling windows of 4 values. From the first 3, we computed the mean, trend, and standard deviation and used the 4th value as the predicted value, helping us capture short-term glucose patterns.
We used mostly standard classification metrics to evaluate our models: accuracy, precision, recall, F1 score, and area under the receiver operating characteristic. For regression models, we used mean squared error, root mean squared error, and mean absolute error. Our results showed that XGBoost models performed the best in terms of predictive accuracy, though the split LSTM in particular gave us valuable insight into how patient features change over time around a dysglycemic episode. Our data splitting technique showed marginal improvement over a standard LSTM that doesn't take initial dysglycemia timing into account, perhaps due to a poorer choice of predictive features. We may have some minor limitations in our deep learning implementation that explains the poorer results of our approach. The univariate LSTM model, however, performed very competitively, and through our implementation could easily be tuned with better hyperparameters for greater performance. Ethics was a key part of our process. We followed the ACS Code of Ethics, kept patient data private, and avoided using any AI-generated code that we didn't fully understand. We maintained version control and clear documentation to ensure transparency and reproducibility.
Throughout the course of the project, we had weekly meetings and regular communication with not only the clients, but also the mentor for our project. This was on top of the meetings we did as an individual group. As such, the structure and consistent communication we had was the perfect basis for our agile workflow with sprint cycles. In our project, dealing with such a difficult database and technically difficult problem, constant communication amongst the group and with the client and mentor was such a large part of our success. We had to make sure that all group members stayed on the same page when it came to complex data analysis and decision making. The difficulty of the project and novelty for us in doing a research project rather than a software development project made our collaboration and commitment to the agile workflow and to the sprint cycles absolutely critical. We're also proud to have addressed a real clinical challenge in dysglycemia in a new manner. The fact that we were able to take on a real-world task made the project one that was very enjoyable to be a part of. As a group, we not only learned a great deal about the research and machine learning process, but also having our work imparted upon a real-world issue, instead of just being done as an individual assignment or personal project, made it very important to us. One of our key takeaways was learning when to pivot. We abandoned complex models that weren't fit to the solution, and instead we chose what was best, and we learned how to deal with timelines in an efficient way. From this, we also set our own deadlines and judged the feasibility of getting things done in a certain time frame. A key part of our work was making the code as modular and reproducible as possible, as well as clear and legible to people who don't have a background in machine learning or knowledge on the issue of dysglycemia. The nature of dealing with health records also required delicacy in the way we conducted ourselves and handling medical records ethically, which we had to adhere to at all times.
For future improvements for this research, firstly, we could incorporate more event types from the Mimic formal database and see how that affects different machine learning models and approaches. Another area for improvement would be to refine our approach to missing and irregular data, as frankly it was fairly crude. Improve our model interpretability for clinical validation, and lastly, the next step would be to in the future would be to validate this research in the real world within a clinical setting with ICU professionals. In conclusion, we built a machine learning system to predict dysglycemia with real clinical relevance as we used ICU lab test data. We combined technical depth with ethical responsibility, gained hands-on experience in data science, ethics, and teamwork. Lastly, thank you for watching our presentation.